or the weight or volume of a particular quantity of material, so you could convey this information to another party in a manner which was understandable and reproducible. Both you and the receiving party must have had a full conception of the magnitude of the quantity transferred before he could have been able to reproduce the length, volume, or weight as you desired. To communicate matters of this nature to one another, we in this country have come to speak freely of distances in terms of inches, feet, yards, and miles, and of volumes in terms of ounces, pints, quarts, and gallons, and of weights in terms of pounds and tons. We have grown up with these quantities, and they have meaning to us. We can convert from inches to feet and from pints to gallons without too much trouble, so long as the quantities are small. But when they get large, we are almost always forced to use a pencil and paper. The units which we in this country use to express our measurements are referred to as customary units, and they are derived from and are closely related to the English system. In much of the rest of the world, people use a different system, a different set of units. Ask a Frenchman how far it is from Brest on the Channel coast to Paris, and he will tell you 510 kilometers. Ask him how much he pays for gasoline, and he will answer 4 francs per liter. He too has grown up with his set of units and understands them. His system is the so-called metric system. He measures lengths in millimeters, centimeters, meters, and kilometers, volumes in cubic centimeters and liters, and weight in grams and kilograms. At the present time, the United States is the only major country in the world that does not use the metric system. This situation of itself is sufficient reason for all of us to be interested in this system. I am Emery Miller. My occupation is Vice President of Technical Operations for Randsburg Electrocoating Corporation. At the moment, I am speaking to you as Chairman of the Technical Council of the Society of Manufacturing Engineers. The Society of Manufacturing Engineers, in conjunction with General Motors Institute and the American National Standards Institute, present Metric Orientation for U.S. Manufacturing Industry. We have brought together a group of gentlemen who are extremely knowledgeable concerning the problems of the metric subject as it relates to United States conversion to this system. They are Mr. Roy Trowbridge, 1971 President of the American National Standards Institute and Director, Engineering Standards Section, General Motors Corporation. Mr. William Burton, Manager of Metric Systems Development of Ford Motor Company. Mr. Kenyon Taylor, President, Beloit Tool Corporation. Mr. Walter Statler, Director, Technical Services, IBM Corporation. Mr. Robert Millitzer, Vice President and General Manager, Excello Parker Corporation. Mr. Robert Eskin, Manager, Product Engineering, Automation and Measurement Division, Bendix Corporation. And Mr. Bernard Sallet, Assistant General Manager, Society of Manufacturing Engineers. In a few minutes, we will ask each of these gentlemen to bring to you their individual thoughts and experiences and views concerning this most important subject. I would, however, stress that in this presentation we are attempting to be informative only. The Technical Council of the Society of Manufacturing Engineers represents all the fields of interest of its 40,000 members. On the council are engineers interested in casting, molding, finishing, tooling, inspection, forming, material removal, material assembly, manufacturing, materials, systems, and management. Any consideration given by this group to a specific topic is bound to reflect the interests of the entire manufacturing and engineering community. For some months, the Council has been considering all aspects of the engineer's use of units in his day-to-day operations. Obviously, both systems, our customary system and the Frenchman's metric system, are practical and provide a ready means of conveying information. They each are being used every day in their own area. When people begin to move from one area to another, either for pleasure or business, then the confusion starts and added difficulty results. If, for example, you happen to be driving an American-made car whose speedometer indicates miles per hour on a German superhighway, you would have a great deal of difficulty trying to decide whether you were within the speed limit of 80 kilometers per hour. Because engineers deal constantly with measurements of this type, their difficulties are greatly compounded. It becomes extremely difficult to use an European drawing scaled in millimeters as the guide for making a device on a lathe which is calibrated in inches. The basic thrust of the Council considerations, therefore, has not been which system, but rather how a better system can be brought into wider use with the least confusion. To this general question, there does not seem to be a one-path ready solution. Wholesale overnight conversion at this point is felt to be much too fast, while side-by-side usage of the several systems over an extended period appears to many to be much too cumbersome. In view of this, the feeling of the Technical Council, and thus the feeling of the Society of Manufacturing Engineers itself, is that an aggressive educational program is in order, so that all concerned will become fully acquainted and conversant with the various systems and recognize their merits. To initiate this campaign, this film has been prepared. Roy Trowbridge will now discuss the present metric situation in the United States. Mr. Trowbridge.
Thank you, Dr. Miller. Beginning in 1965, with the declaration of the British Board of Trade that it was desirable for British industry to begin to adopt metric units until the metric system became the primary system of weights and measures for the country, there has been one declaration after another from other British Commonwealth nations until all except a few outposts are now either in the process of converting to metric or are committed to do so. Thus, except for the United States and a few comparatively underdeveloped countries, all other countries of the world are now using metric measures as their principal measurement language or have committed themselves to metric usage, most with definite timetables for completion of the changeover. In August of 1968, on authorization of Congress, the National Bureau of Standards initiated a 3-year study to determine the impact of increased worldwide use of the metric system on the U.S., to appraise the feasibility and practicability of increasing use of metric weights and measures in the U.S., to study the feasibility of retaining and promoting dimensional or other engineering standards based on customary measurement units of the U.S., and to evaluate the cost and benefits of alternative courses of action which may be feasible for the U.S. The metric study report, issued in July 1971, concludes that the U.S. should change to the metric system through a coordinated national program. In submitting the report to Congress, Secretary of Commerce Stans agreed with the recommendation of the National Bureau of Standards, making the following major recommendations: that the United States change to the international metric system deliberately and carefully, that this be done through a coordinated national program, that the Congress assign the responsibility for guiding the change and anticipating the kinds of special problems described in the report to a central coordinating body responsive to all sectors of our society. that within this guiding framework, detailed plans and timetables be worked out by these sectors themselves. That early priority be given to educating every American school child and the public at large to think in metric terms. That immediate steps be taken by Congress to foster U.S. participation in international standards activities. That in order to encourage efficiency and minimize the overall costs to society, the general rule should be that any changeover costs shall lie where they fall. That the Congress, after deciding on a plan for the nation, establish a target date 10 years ahead, by which time the U.S. will have become predominantly, though not exclusively, metric, and that there be a firm government commitment to this goal. Although Congress has not yet acted on the report, it is likely that the U.S. Department of Commerce will be identified as the central coordinating body. In any event, all technical, professional, and trade groups will form individual nuclei for carrying out necessary education and coordination. The 10-year timetable specified by Secretary Stans may be too short for some, too long for others. In addition, it is likely that there will be many measurement usage areas which will remain unaffected by a major change to metric in the U.S. Much will have to be done to establish priorities and to assure, on the one hand, that unmindful foot dragging is avoided, and on the other hand, that the voluntary program does not become coercive, calling for unproductive change of measurement practice solely for the sake of change. No matter how the change is coordinated, and regardless of timing, practically all change will have to be preceded by education of those affected and by development of engineering standards which make use of metric units. Whether or not these standards are simple translations of existing national standards or are new standards made to a metric base will be determined through the interaction of industry, commerce, consumers, and the relative importance of the standards to domestic or international trade and commerce. Using its Metric Advisory Committee, the American National Standards Institute, known as ANSI, working with its members, will promulgate the necessary fundamental rules for metric usage. Through its member bodies and technical advisory boards, ANSI will assist in the conduct of studies and will help establish appropriate standards development timetables in the many disciplines which will require new metric voluntary engineering standards. Obviously, a major educational effort in the U.S. is required if we are to continue to communicate with the metric world, regardless of whether our individual technical disciplines convert to metric. As stated by Dr. Miller, it is for that purpose that this SME program has been developed. Mr. W.K. Burton, Manager of Metric Systems Development for Ford Motor Company, is well qualified to introduce us to the metric system by tracing some of the more recent developments which have led to worldwide recognition and almost universal usage of the Système International de Unités, known as SI. Bill?
Thanks, Roy. If after having lived in an inch-pound environment most of your life, you feel somewhat apprehensive about the idea of using metric units of measure, relax. It's only natural. That is, we sense a subject that is in conflict with the information for which we have been previously brain programmed by repetitive use in daily life. This reaction can be overcome by sufficient self-discipline to learn to use the metric system. This is accomplished through repetitive practice in the application of metric units of measure until a metric program in comparable magnitude is retained alongside the existing inch-pound program in our respective capacities. Only after this has been accomplished will we as individuals be capable of comparing the relative merits of the two systems of measure. During the period of metric program development, you must constantly avoid the temptation to make lasting, important decisions or to take relative positions prior to your metric program maturity. Otherwise, be prepared to encounter embarrassing and costly mistakes. Since ancient times, man has groped for the ideal measuring units with which to specify consistent amounts of the various physical quantities that comprise our total environment. We now have 6 basic quantities: length, time, mass, temperature, electric current, and luminous intensity. Cut it. Exemplifying a partial diagram of the genealogy of a measuring system, we find that 4 basic quantities, length, time, mass, and temperature, with their interrelationship to form derived quantities, satisfy most of our mechanical needs. Of the 4 basic quantities, length is by far the most involved. Following length through its interrelationship with time and mass, we observe that length squared gives us area, and length cubed gives us volume or capacity. Length divided by time gives us speed or velocity. And if we divide speed by another unit of time, we get acceleration. To involve mass with acceleration takes force. If we apply force to area, we get pressure or stress. And if we apply mass to volume, we get density. You will note that the quantity temperature does not relate to any of these derived quantities. Derivatives of the quantities temperature, electric current, and luminous intensity appear in the more complex total genealogy structure, where more than 80 derived quantities exist to satisfy all the needs of science and engineering. It isn't likely that any of us will require the use of all of the quantities in our normal daily activities. There are now several systems of units of measure in use throughout the world that express precise magnitudes of each of the quantities, even though the magnitudes generally vary from one measuring system to another. For instance, the yard for length in our U.S. customary system is not equal to the meter for length in the metric system. These variations proliferate as we progress through the derived quantities of the genealogy structure. Since there are several metric systems in existence, there are variations among these that result in similar conflict with precise communication. To eliminate these variations that confuse international communication, the treaty countries of the General Conference of Weights and Measure, CGPM, in 1960, through resolutions and recommendations, adopted a new metric measuring system entitled the International System of Units, and this is to be referred to as SI in all languages. I recommend for your guidance this National Bureau of Standards Special Publication 330, which is the official English translation of the resolutions and recommendations of the General Conference of Weights and Measures regarding the SI units. It is available from the U.S. Government Printing Office for 50 cents. The 6 units for the 6 base quantities are meter for length, kilogram for mass, second for time, ampere for electric current, Kelvin for temperature, and candela for luminous intensity. On this chart, we have applied the SI unit symbols to their respective quantities. Meter for length, square meter for area, cubic meter for volume, second for time, meter per second for speed, meter per second squared for acceleration, kilogram for mass, Newton for force, Newton per square meter for pressure, kilogram per cubic meter for density, and Kelvin for temperature. SI also includes a range of multiples and submultiples of 10 with prefix names that can be added to the base units to provide logical magnitude. Of utmost importance is extreme care in the use of capital and lowercase letters of the alphabet. They must be applied exactly as specified by the General Conference of Weights and Measures. There can be no deviation from the recommendations regarding names and symbols without penalty of error. The International Organization for Standardization, ISO, in cooperation with the International Bureau of Weights and Measures, has developed and published Recommendation R-1000, covering the rules for the proper use of SI units with a selection of the decimal multiples and submultiples. This is the international reference document on the proper use of SI, and we strongly recommend that you follow its direction consistently. R-1000 is available from the American National Standards Institute, the United States member of ISO. R-1000 is kept current through the efforts of ISO Technical Committee TC-12. Now, Mr. Kenyon Y. Taylor, President of Beloit Tool Corporation, who has been deeply involved in the development and production of metric tools for manufacturing, will explain the differences between our customary U.S. units and SI, with some of the conversion values and size implications. Ken?
What is the metric system? The metric system is a structured, rationalized, and coherent set of units with a simple language and definite relationships between length, volume, and weight that does not exist under our present inch-pound system. Let us now look at the basic metric system of measurement that will be used by 92% of mankind by the year 1975. How do we measure the length of this line? We divide into convenient units, count the units, and we have the length. Should these units be the length of a foot, the length of a yard, or 1/12 the length of a foot? As you know, these are the units available in our present system. Because our English system has been borrowed from many different systems, we have the inch, 12 to a foot, 3 feet to a yard, and 1,760 yards to 1 mile. These are awkward figures, not related to each other or to problems of volume and weight. Under the simple metric system, we have a definite relationship between length, volume, and weight, because the system was planned that way. And as we shall see, the metric system enables us to work easily with any length, any volume, any weight in the world. What is a meter? If the distance from the North Pole to the equator was divided into 10 million equal parts, we have 1 meter. It is equal to 39.37 inches and is about 10% or 3 3/8 inches longer than our yard. Unlike the mile, yard, foot, and inch, larger and smaller units of the metric system always change in multiples of 10, or the decimal scale. For lengths longer than the meter, the Greek prefixes Deca, Hecto, and kilo are used. 1 decameter equals 10 meters. 1 hectometer equals 100 meters. And 1 kilometer equals 1,000 meters. Therefore, 10 meters are called a decameter, 100 meters a hectometer, and 1,000 meters a kilometer. For a length smaller than a meter, the Latin prefixes deci, centi, and milli are used for tenths, hundredths, and thousandths. 1 decimeter equals 1/10 of a meter. 1 centimeter equals 1/100th of a meter. And 1 millimeter equals 1,000th of a meter. These same prefixes are used for weight and volume. We use units of length to determine area. The metric unit of area is the square meter, or the area of a square 1 meter on each side. For measurements of volume, we have the cubic meter. It is a cube with the sides each 1 meter in length. If we build a container 1/10 of a meter, or 1 decimeter on each side, the amount of liquid it will hold is slightly more than 1 quart and is called a liter. The weight of 1 liter of water is equal to 1 kilogram, which incidentally is the basic unit a housewife would use in buying potatoes. 1 kilogram is equal to approximately 2 1/5 pounds. Again, with the simple prefixes, 10 liters would be a decaliter, and 1,000th of a liter would be called a milliliter. A container that has sides 1 centimeter long is called a cubic centimeter and will hold 1 milliliter of water. This unit makes for easy transition to metric weights, for the weight of the amount of water in 1 cubic centimeter is the basic metric unit of weight, or 1 gram. Now we can see the simple and convenient metric system has a direct relationship between length, volume, and weight. Since all metric measurements are written decimally, calculations are greatly simplified. 15.50 meters means 15 1/2 meters, or 15 meters plus 1/2 of 100 centimeters, or 15 meters plus 50 centimeters. Using the metric scale, any denomination may be changed to a higher denomination by moving the decimal point to the left. For example, to determine the number of kilometers in 1,550 meters, we move the decimal 3 places to the left and read the result as 1 kilometer and 550 meters. Any number may be changed to a lower denomination by moving the decimal point to the right. For example, to determine the number of centimeters in 15.5 meters, we multiply by 100, or move the decimal point 2 places to the right. Therefore, 15.5 meters equal 1,550 centimeters, or 15,500 millimeters. To convert grams to milligrams, we multiply by 1,000. To convert grams to kilograms, we divide by 1,000. As we learn the metric system, we realize that it is based on a natural standard. It is convenient to work with this decimal system, and that measurements of length, area, volume, and weight have a direct relationship that does not exist between our miles, gallons, and pounds. During the early stages of change to the metric system, and until complete conversion of both language and measurement is accomplished, it is necessary to consider approximate comparisons. How do metric units compare with our English units? A meter is about 3 3/8 inches longer than our yard. A kilometer is about 5/8 of our mile, and a highway sign that reads 80 kilometers per hour is the equivalent of 50 miles per hour. A liter holds a little more than a quart of liquid. A gram is a small fraction of our ounce, and 1,000 grams equals about 2 1/5 pounds. All of these and many more are easily described and defined in metric terms of the meter, the liter, and the gram. Now Mr. Walter Stadler, Director of Technical Services for International Business Machine Corporation, has some interesting suggestions covering methods of metric conversion.
Thank you very much, Ken, for an excellent presentation. This seems like a good time for a break in the program. Please stop the tape and we'll be back with you shortly. Welcome back. I'm Walt Statler. The preceding speakers presented to you an authoritative chronology and description of the metric system. I now should like to discuss with you various methods of converting to the metric system. The ideal way of becoming proficient in the use of the metric system is to think metric. This means thinking primarily in metric terms rather than in customary terms. It is analogous to becoming fluent in speaking a foreign language. If you mentally structure a sentence in English and translate it in your mind to French before speaking, you are not proficient in French. You must think in terms of the language in which you are going to speak. These illustrations show you some of the common conversions of customary units to metric which you encounter in everyday life. To be sure, people cannot think metric until they have had some educational exposure to the system. This might be in formal class instruction in high school or college. Others can become familiar with the system through technical society programs, adult education classes, technical magazines, newspapers, and television. The substitution of metric units for non-metric units now in use without change in standard dimensions or tolerances is known as soft conversion. This can be carried a step further by indicating on engineering drawings and specifications both customary units and metric equivalents. This is commonly called dual dimensioning. Up to this point, we have only considered conversion in which metric units have been substituted for customary units. We shall now consider the design of parts and products using the metric system as the base. Customary unit equivalents may or may not be shown. At the same time, sizes, tolerances, specifications, and standards must be established, again, on a metric base. This is called hard conversion. The full potential of the use of the metric system cannot be achieved unless standards based upon the metric units are established. These standards must include both parts and materials. For example, in the United States, steel plate and bars in the full range of sizes are covered in increments of 1/32, 1/16, 1/8, or 1/4 inches, whereas in metric countries, the increments are usually in 1, 2, and 5 millimeters. If these materials were not available as standard items manufactured in metric specifications, it would be pointless to design parts in metric dimensions. Another method of converting in the metric system is to select a suitable product prior to actual design, and from its inception use only metric units for dimensioning as well as for engineering specifications. Simultaneously, manufacturing can plan for the production of the product when it is released from engineering design. In conclusion, major components and end products requiring special tooling should be specified in units based upon the metric system only after new metric tooling, standard parts, and raw material are readily available at reasonable cost. Mr. Robert Militzer, Vice President and General Manager of the Excello Parker Corporation, will now discuss practical examples of metrication as applied to tooling. Bob?
Thank you, Walt. Now that our previous speakers have given us such an excellent overall viewpoint of the relationships between metric measurement and our present customary measurement system, let's see just what this change would mean to the average metalworking shop. So many of us in the Society of Manufacturing Engineers are engaged in the application of machine tools. It might be helpful if we examine the practical aspects of metrication on the elements of these machine tools. Metal cutting operations are always made up of a relative movement between the cutting tool and the workpiece. In most cases, rotative movement is applied to one element, the tool or the workpiece, while lineal motion is utilized for consecutive passes of stock removal. Critical factors in the efficiency of any metal cutting operation are the speed of rotation and the feed rate of stock removal per revolution. Probably one of the most frequently used terms of reference which will be affected by the move to metric measurement is that of feeds and speeds. These factors are presently specified in inches per minute or feet per minute, and through common use have become part of the very thought processes of every manufacturing engineer, tool maker, machine operator, and job setter. There are many charts, nomographs, and tables that are used by cutting tool specialists to determine proper feeds and speeds. These terms will be specified in millimeters per minute under the metrication program, and there will be a need for all new nomographs, charts, and tables to be made available to these engineers, machinists, and tool makers. More importantly, and yes, admittedly more difficult, the very thought processes of these technical people will have to be adapted. When troubleshooting or setting up a machine operation, we must now rationalize our feeds and speeds using millimeters instead of inches. Here is an example of one of the most modern machine tools made. It is a 4-axis horizontal spindle, fully automatic, numerically controlled machining center. This machine can perform all conventional metal cutting operations, and it takes its complete operational command program from this machine control unit. The digital readout is showing the exact dimensional moves made by the index table in the X and the Z axis, and the spindle in the Y axis. The readout is shown in decimal inches. The movements the table or the spindle make are actuated by motor-driven lead screws. These lead screws are presently dimensioned in a specific number of inches of travel per revolution of the screw, and the numbers on the readout are representative of decimal inches of table or spindle movement. In a metric system of measurement, the lead screw would be dimensioned in millimeters per revolution, and the readout would show millimeters of travel or spindle travel. As we can see, the fundamental change to the utilization of machine tools in the metrication program will be in the calibration of the equipment, not in the operation thereof. Our present inch-based machine tools can be used without modification to manufacture metric dimensioned products. This could be accomplished either through a dual dimension drafting system, a conversion table supplied to the operator, or performing the actual calculations for conversion at the machine. But a far more efficient approach is to modify the machine tool to utilize metric system calibrations. This is accomplished through the supplying of new lead screws, change gears, readout dials, and scales or other dimensional control components. Basically, our machine tools will be completely unaffected by the move to metrication. The machine operation will be exactly as before. The results produced from the equipment will be identical. The functional operation will be unaffected. Previously learned guidelines on cutting tool operations will not in any way be obsoleted, but our terms of reference will certainly be vastly different, and every competent manufacturing engineer must prepare himself to deal with this new technology. Now, Robert Eskin, Manager of Product Engineering for the Automation and Measurement Division of Bendix Corporation, will discuss the effect of metrication on the field of measurement. Bob?
The very core of the metric system is the internationally accepted standard of length, the meter. This standard is and has been the accepted standard in the U.S. since 1866. Since its original acceptance, the meter has undergone several revisions in the definition, with each revision attempting to more accurately define its absolute value. Currently, the meter is defined in the terms of wavelengths of light emitted by a specific light source. By this definition, it is possible to duplicate this standard to an accuracy of 1 part in 100 million at any place and at any time. However, of primary importance is the standard itself is indestructible. The customary unit of measure in the U.S. is the yard, with subdivisions of feet and inches. However, the definition of the yard is defined in terms of the international standard meter. Consequently, all the measurements made in inches are directly related to the meter. The numerical value of this relationship is 1 inch equals 25.4 millimeters exactly. This ratio is an important number to keep in mind and is extremely handy when converting inches to metric or vice versa. Inches are converted to millimeters by multiplying, and millimeters converted to inches by division. Using this method allows exact conversion to any desired accuracy. As the metric system increases in use, part drawings and specifications will become more prevalent with dual dimensioning. This requires a dimension to be stated initially in either inches or metric and followed immediately with its converted value in brackets. The choice of inch or metric for stating the initial dimension would be based on the system in which the work had originally been done. When converting from one system to another, 3 choices are available: exact, rounded, and rationalized. For example, a standard sheet of tablet paper measures 8.5 by 11 inches. Converting to exact millimeters would be 215.9 millimeters by 279.4 millimeters. This could be rounded to 216 by 279 millimeters for general discussion or talking purposes. However, if one were going to establish a new standard size for metric tablet paper, it may be logical to rationalize the dimension to 220 millimeters by 280 millimeters. Several booklets are available, such as the ASTM Metric Practice Guide with rules for conversion. Using the metric system does not in any way change the fundamental concepts or good practices for measurement. What does change is the unit values in which the measurements are reported. If a tape measure were used to obtain the width dimension of a room, we may find the results of 17 feet 6 1/4 inches. To report this dimension in a common unit, it is necessary to multiply 17 times 12, then add 6 1/4, and arrive at 210 1/4 inches. If the tape were metric, the results would be 5 meters 34 centimeters. With the base 10 metric system, this is quickly reported in meters as 5.34 meters. It should be noted the convenience of stating a value in any of the basic units of the metric system while minimizing the chance of error. This results from the fact that none of the digits change in the final answer, only the placement of the decimal point. One of the fundamental measuring tools in manufacturing is the micrometer. If we compare inch mics with metric mics, we find the basic calibrated graduations on the barrels and thimbles. However, we notice a difference in the calibration marks. In the inch mics, the graduations are 25 thousandths on the barrel and 1 thousandths on the thimble. On the metric mic, we find a 0.5 millimeter on the barrel and 0.01 millimeter on the thimble. Both mics are read in identical manners. The inch mic reads 0.262 inches. The metric mic reads 6.65 millimeters. Other measuring tools have dual calibration scales. For example, the ordinary machinist scale is available with both inch and metric calibration on the same scale. Other more sophisticated measuring tools have many types of scales. Dial indicators, pneumatic gauges, electronic gauges are all available with scales in either inch or metric or with dual calibrations. Some electronic gauges are available with the option of readout in inches or millimeters by the flip of a switch. Measuring devices using digital displays, such as coordinate measuring machines, can be obtained with either inch or metric or with built-in multipliers that allow readout in either system. With all the various measuring tools available in either inch or metric, a good rule to follow is use inch calibrated scales when measuring in inches and use metric calibrated scales when measuring millimeters. Metrication does not change fundamental measuring and gauging concepts. If anything, it will improve the results obtained due to the use of a less ambiguous system related to the base 10 and its direct relationship to the international standard. To suggest some thought-provoking areas for courses of action by American industry, here is Mr. Bernie Talat, Assistant General Manager and Manager of Technical Activities for the Society of Manufacturing Engineers. Bernie?
Dr. Emery Miller told you how the Technical Council of the Society of Manufacturing Engineers has closely followed the relationship of American industry and the use of the metric system of measurement by the rest of the world. In order to do this, the Council used the input from some 70 organized vertical disciplines in its technical divisions, which disciplines cover the entire spectrum of manufacturing and manufacturing engineering. As it watched the changeover of major nations, which has resulted in almost total metric saturation of the world outside the United States, it became increasingly apparent that major segments of American industry would expand their use of the metric system, and that such expansion could take place according to a reasonable timetable. Hopefully, this increased use would take place on an orderly basis in an atmosphere not charged with emotion, and that the determination to change would be voluntary based on the degree of benefit to each segment of industry. Our Technical Council recommended, and our Board of Directors approved, the following policy statement for the Society of Manufacturing Engineers. To serve the best interest of its membership and industry, the Society of Manufacturing Engineers endorses the use of the International Metric System of Units. The intent of this policy is concerned only with education in and the use of SI units. It is not designed to cause change in established standard dimensions, tolerances, or specifications. You have heard a cross-section of the leaders of American manufacturing who have talked to you about the basic metric system. They have talked about its differences from the English system, the ease of its use once understood, and they have scratched the surface of some of the very real problems of using this system. You have also heard a very brief history of the events which bring us to the point we are today, where seemingly an expansion in the use of the metric system will occur. This program was not designed to cover the infinite aspects of metrication, nor to answer all questions which you, your industry, your management, and your technical people may have. Rather, it was designed to be the first step on Mr. Burton's ladder of brain programming, which ultimately will lead you to the same understanding of the metric system that you now have of the English. You must follow through with your own in-depth studies of your own particular situation, and only on the completion of these studies will you then be able to make a meaningful decision concerning the extent to which use of the metric dimensions will fit your own operation. Now, what are the steps and what is the need to know to reach this point of decision? First, technical and professional people must come to a working knowledge of the metric system. Secondly, these same technical and professional people must apply this knowledge to their own product, their own industry, and their own manufacturing capability. Third, they must make objective and alternative recommendations to their management, which must itself be concurrently learning to understand the metric system. Management must bring its own level of understanding to a comfortable position. Fourth, management must coldly and unemotionally make its decision to wholly, partially, or not at all expand its use of the metric system. Fifth, technical and professional people must stand ready to develop the programs based on this decision and to implement the expansion with a minimum of disruption. Sixth, it means that the technical and professional organizations will have to act as the coordinating groups to supply the technical input for the almost complete revision of manufacturing standards and product standards that will be necessary. Technical groups and committees must supply this knowledge. The technical and professional groups must certify its consensus, and then they must be recommended to the American National Standards Institute for promulgation as American National Standards. Contrary to popular conception, some segments of U.S. industry, particularly the multinational companies, have made use of the metric system for years. Some segments feel comfortable with a dual system. There will probably always be some of these segments to whom conversion is no advantage, and these segments are not likely to change. Now, what does this mean in an overall national program? It means simply this. A major program of education must be carried out by the technical and professional organizations which will assist the technical and management groups with their understanding of the problem. It means that these groups must use their conferences, their technical gatherings, their publications, and all modern means of dissemination to transfer both understanding of the system and already existing technical expertise to those who have not previously had such an opportunity to learn. The Society of Manufacturing Engineers was a pioneer in leading the technical and professional community into the areas of environmental pollution, occupational health and safety, certification of technical people, etc. It now stands ready to provide a strong and dedicated technical information base and guidance to the leaders of American industry in the matter of metrication. It will assemble the expertise of some 45,000 members for all areas of manufacturing and manufacturing engineering and make it available throughout the United States in its major series of expositions and technical programs. To do this, it will need, as will the other professional groups, the complete support of American industry. If this program has made you thoughtful concerning the effect of a metric conversion on your own operation, and if it has indicated to you the areas where greater in-depth understanding is necessary, it has more than accomplished its purpose. The Society of Manufacturing Engineers and the American National Standards Institute are ready to assist. simply address a request to me at the Society of Manufacturing Engineers or to Mr. Donald L. Payton, Managing Director of the American National Standards Institute. Many fine publications are available from either of us and from some of the companies involved in this program. Copies of this tape are also available from either the Society of Manufacturing Engineers or the American National Standards Institute for purchase if you wish to use it with your own personnel. And now, as we conclude, let me express the appreciation of the Society of Manufacturing Engineers for the opportunity to work with the following groups in the presentation and preparation of this tape.